How are you, everybody who is watching this video? I'm very happy to have you today, and I would like to take this opportunity to welcome you into workshop 9, when we are going to do the measurements and also to display the waveform of the linear power supply. My name is Olenjolain, and I would like to tell you that these programs or this course or this video or this workshop, actually I have prepared it to become a fundamental concept to the different students. So whether you are ordinary diploma students or you are undergraduate students or you are O-level students, these contents might be helpful, especially if you love electronics engineering or if you love telecommunication engineering. So I would like to take this opportunity to ask you that to remember or to refer or to go through the previous workshop in order for you to capture about what we've discussed, because this is the continuations. We had the workshop number 1, and then this is workshop number 9. So if that's the case, I think that it's better for you, if you're watching this video, it's better to have the materials, the measuring instruments, the components that we are going to use in order to conduct this practical. So it's better to have and make a follow-up. We'll be going step to step, but our measuring instruments today will be focusing is digital oscilloscope. So if that's the case, I'll have some local students here, local engineering students who are doing electronics and telecommunication engineering at Dar es Salaam Institute of Technology. So let us acknowledge them and then start the business. Good afternoon, class. Yes. Are you ready for today's workshop? Yes. Okay, so let us go to the business. So the first thing which I want to introduce to you is about the materials and the instrument that we are going to use for this workshop. So firstly, we are going to have a power cable. This is the power cable. Actually, that's where we are going to take a power from the main AC. And then this is the step-down transformer, which can take 220 volt and provide 60 volt if you use as the non-center the step-down transformer, or it can provide 12 volt. So, again, we are going to have a digital multimeter, however, that we are not going to use it effectively because in previous workshop we have been using it. And then we are going to use, we have a breadboard where we are going to build it. This will be like a land where we're going to build our house. Then we are going to have almost 11 components. We are going to have 4 diodes to build it, the bridge rectifier unit. Just at implementation, you can implement by using these 4 diodes. So these are the 4 diodes. So these are the 4 diodes. And then we are going also to have 2,200 microfarad with 35 volt. This is the electrolytic capacitor. You may have even one of the 1,000 microfarad. The only thing that you have to make sure that the operating voltage or the rated voltage should be 25 volt. We are going to also have a voltage regulator, which is LM3805. We are going to have a limiting current resistor that will limit the current flowing through the light emitting diode. And also we are going to have a light emitting diode. This will indicate the block of the load. So we are still applying or using the same principle that the linear power supply has 5 blocks. The first one is step-down transformer. The second one is bridge rectifier or rectifier unit. The third one is filter unit. And the fourth one is voltage regulator unit. But the last one is load. So what are we going to do today? So today we are going to focus on the 2 parameters or the 2 things. I told you that engineering can be summarized in 5 terms or in 5 terminologies. Engineering can be represented in terms of numbers, in terms of formula, in terms of equation, formulas and equation, in terms of diagrams, in terms of tables, and in terms of of graphs. So in previous workshop, we've been dealing with numbers, especially in terms of calculation. We've been dealing with the formula, and if you do remember that, we had a formula that showed a relationship between root mean square voltage and the maximum voltage, or root mean square current and maximum current. But we had also another formula which actually that was teaching us how we can compute the output voltage from the bridge rectifier, because there's a potential barrier or there's a potential drop when the currents or when the alternating voltage flows through the diode. But again, we have another formula that we've used, especially in computing the capacitance of the electrolytic capacitor. which we call the ripple factor equation. So we have discussed about how can we develop numbers in engineering, how can we develop formulas or recall the formulas that we had in mathematics or in science, because in engineering we are using formulas from science and OT and mathematics, right? Right? Okay. Then we drew some diagrams, block diagrams, thematic circuit diagram, we drew them. So I have showed you how we develop diagrams in engineering. But also in previous workshop number 8, we have used the digital multimeter to do measurements, and especially for the voltage. We didn't discuss about the part of the current. We had a focus on the voltage. So today, I'm going to show you the 5th terminology of engineering, which is the graphs. We had the theoretical graphs that we have drawn in the linear power supply. So these actually are the waveform. But the good thing that the oscilloscope that we are going to use, it can provide the nature of the waveforms, and also it can provide the measurements. So it means that the digital oscilloscope can act also like a voltimeter in some cases. It can act as a frequency meter. So it has a built-in frequency meter. It has built-in voltimeter in order to measure some important parameters that we use to measure by using the digital multimeter. So if that's the case, I would like to introduce you about the core measuring instrument that we are going to use today. So we have, in electronics, we have something we call it oscilloscope. Class A oscilloscope. Say oscilloscope. So we have two types, main types of oscilloscope. We have analog oscilloscope like this one. It's heavy. This they call it a workbench. But it does not mean that all analog oscilloscope are huge like this one or heavy like this one. No. This is the heavy duty. When you say heavy duty, means when you use it, you can use it, and even sometimes it has something called the short circuit protection. RASA. Then this is the analog oscilloscope. So it means that it displays the waveform, but also it can provide the measurements of the some parameters of the voltage and sometimes of the current, if you are focused on the current. But again, we have another one, which is actual modern. This is digital oscilloscope. So it's this digital oscilloscope, it's actually advanced and it has so many functionality compared to analog oscilloscope. So for this workshop, we are going to use this digital oscilloscope. And you have to keep focus on the screen, because on the screen and then on this menu, this is the menu section. So you have two main sections. We have menu section and also you have the display section. So menu sections, this is the point where I will interface with the digital oscilloscope to ask it to give me some particular information. And then the display is going to display what we have fed. But remember that oscilloscope, whether analog or digital, it's output measuring and testing instrument. So it needs something to be given at its input. Okay? And I want to tell you, as a beginners and as engineers, there's a lot of information which have been hidden. This digital oscilloscope has so many functionality more than you could think. So I will not discuss in detail about how to use this oscilloscope, but I'll just teach you some key concepts that we need in order to achieve the objective of this workshop, to show the nature of the waveform at the graphs. Are we together? Are we together? So to use this oscilloscope, you need a power cable. So this is the power cable to provide power. And then you have to connect it at the back. I think that this is simple, because you might ask your questions to yourself how we can power it. So when you connect to the power, this is the on-off button. This is the on-off button. So on-off button. And then another part, I have explained about the display section and also the menu section. So how can we connect the input to the oscilloscope? We need this, we call it BNC connector or BNC probe. BNC OT. So it has two tips. Martha, it has two tips. So this is the positive for the positive tip, and this one for the ground. So this we call it a BNC connector because you have to figure it. And this digital oscilloscope, it has two channels. It has channel number 1 channel number 2. So you may connect the BNC cable in channel number 1 or in channel number 2. It depends which channel you want to use to do your measurements. Are we together? Are we together? Yes. Are we together? Yes. Okay, so I think it is clear. Before I begin to set up the oscilloscope and then we come back to building the circuit, I would like to give you a chance. If there are any questions about what I have explained to you and presented to you, you may ask before I continue. Is there any question? No. So now let us turn on our oscilloscope. So students, listen and keep focus on the screen. Collins. So now our digital oscilloscope is on. So when it is on, you see that there are some buttons, or there's some amount, there are some buttons which contains light emitting diode. So this one is run or stop button. There's this function. But you can see the waveform here. So this is the, we call it the center of this digital oscilloscope, where you see the yellow. So the first channel, the first channel will use the yellow color to present the waveform. And the second channel, or channel number 2, so near channel number 2, will display the waveform by using a blue color, a faint blue color. Are we together? Are we together? So right now, you can see this one because it's channel 1 which is on. Whenever you change or you configure, you set the digital oscilloscope to be out to operate or to receive the signal from the channel 1, then you'll see that channel 1 main contains some light. So for now, this is the channel 2 main. So whenever you don't see any light in the buttons of channel 2, it means that channel 2 is off. So if we turn it on right now, you could see that. Again, we have another center waveform. Okay? We have another center waveform. So this one representing, now channel 1 and 2 are on. You may use one channel or you may use 2 channels. So it depends to the experiment that you want to figure it out. Are we together? Are we together? So, how are we going to set our digital oscilloscope? It's not difficult. The first thing, these BNC cables, they have built-in internal resistance. And this built-in internal resistance, you as the user, you can use it or you can multiply it because there's a number here. There's a times 1 and there's a times 10. So it means that it depends to the type of the oscilloscope that you are using. Some of the digital oscilloscope, they need you to set your probe attenuation. This we call it probe attenuation setting. So it means that some of the oscilloscope might need you to set your probe or the probe attenuation setting to be in 1 or times 1. And some of the oscilloscope, digital oscilloscope or even analog oscilloscope might need you to set the attenuation signal in times 10. Are we together? So according to the manufacturer's mind, which is actually explained in the user manual of this digital oscilloscope, which its name is called the Hanteki MS or 5202D. So according to the manufacturer or user manual of this digital oscilloscope, you have to make sure that the probe attenuation setting should be times 10. So how can you change? There is a switch. Cancasia is cancasia. There's a what? It's a switch. So if you press it to down, it means 30, then this is times 10. When you press it up, then that is times 1. Are we together? I will give you the oscilloscope. You will see that buttons to change the attenuation setting of your BNC probe. So you have to set it in times 10. If you don't follow this instruction, if you set times 1, you are going to get completely different readings. And you will never accomplish what you intended to accomplish. Are we together? Are we together? That is the first thing I have to present to you. The second concept that I have to present to you, we have to make sure that we have to do the default testing of the digital oscilloscope, or we have to do digital setup, means default setup, or we have to set our digital oscilloscope before we connect the input signal. How do we do that? So you say that let us use channel 1 to avoid, just to simplify the concept. So you have to connect our probe into channel 1. So you connect it and then you tie it for certain extent. So right now our probe is connected to the channel 1. So I've connected to the channel 1. Then the next step after connecting the channel 1, the manufacturer has given you the default signal. And this default signal, it has a maximum voltage of 5 volts and frequency of 1 kilohertz. And also, if you check this button at this point, you will see also there's a symbol of the square wave, of the pulse, not a square wave, of the pulse. So if we connected our probe into this, we call it probe component part, or probe component terminal, then we expect it to have the input signal, the default input signal from the oscilloscope, in order to set up our digital oscilloscope before we feed the input signal. May I repeat? Okay. I say the second process that we are going to do now, we are going to set our digital oscilloscope. The way that we are going to set our digital oscilloscope, we have to connect it first of all the BNC probe, or the probe, into one of the channels, whether channel 1 or channel 2. But the goodness, this digital oscilloscope comes with the 2 probes. So you may connect one probe in channel 1 and be connecting another probe in channel 2. Right? You are not limited. It depends about the measurements that you want to do. And then, after that, the next step now, which I told you that, we have to configure, or we have to set our digital oscilloscope. And the way that we are going to set it, according to the user manual of this Handtech digital oscilloscope, the manufacturer said that in order to set this digital oscilloscope, you have to connect it, this probe, into the probe component part. Within this probe component part, there is a circuit which acting like a signal generator that can generate the default signal. And that the default signal, the nature or the waveform of that default signal is pulse. It's not sinusoidal, it's not a square wave, it's not sawtooth, it's not triangular, it's not any kinds, it's not ramp signal, it's not any other signal that you may get in the functional generator. So the nature of the waveform is a square wave. Is what is pulse. Say pulse. Say pulse. Then that pulse will have the maximum voltage of 5 volts. But also the frequency of that pulse will be 1 kilohertz or 1000 hertz. Okay? So this one is actual to set up. We are setting our digital oscilloscope before you feed your input signal. You want it to study the waveform or the nature of the waveform in that signal and do the measurement. Are we together? Are we together? So now I'm going to connect the BNC in order to do the default setting. So I have just to press in this way and then connect it here. So you leave it. Then I connected this groundy probe into the ground terminal. So now I have finished the connections. I have connected the BNC connector into the channel 1. And then I'm taking the input from the part of the oscilloscope in order to feed into the channel 1. Are we together? So the manufacturer said that the nature of that signal will be what? Pulse. The maximum voltage will be what? 5 volts. Then another thing, the frequency of that signal will be 1 kilohertz. Are we together? Yes. Are we together? So then let us come to our display. So when you go to our display, we have something looks like what? Square wave. That's the square wave. It just has some spikes because of some noises. Are we together? But maybe the shape is not good for you. So then we are going now to do the we are going to tell you the digital oscilloscope to use the built-in software in order to set itself automatically. So I'm going to press these buttons of auto set. Say auto set. Say auto set. Auto set. Auto is abbreviation of the word automatic. Right? Right? So when you press these buttons means we are setting our digital oscilloscope automatically into the default setting. And why are we doing this process? Because sometimes you might say that the digital oscilloscope does not work or does not display the nature of the waveform and the measurement that are expected. So that's why the manufacturer gave you the accurate signal, the measured signal, which does not have any challenge. Are we together? Are we together? Are we together? So once you do that setup, then now you can feed your input signal. So we are going to press this button and wait for some few seconds. So let us press. Then if you press, you wait for a short time, then you see the nature of the waveform has changed. Do you see what happened? Eh? Okay. So maybe the width of 40 of the waveform, or maybe the width of the waveform. So we are going to another place now. We are going to set this signal, the waveform that we have, which is the 40 waveform. So maybe the width of the waveform is not the one that you want. So now we are increasing what? We are increasing frequency, we are reducing period. Right? If you rotate these buttons, it will be written as what? Second per division. If you rotate in this way, you are going to increase what? Increase period and reducing the frequency. So go back to the display. So now you could see that the periods has been increased, the frequency has been reduced. Are we together? Are we together? Okay. So then let us maybe choose this one. So we don't know the magnitude of that pulse. The next step, we have to press another button. Student, I ask you to concentrate and look on the blackboard. Say fine. Then the next step now, we want to get the measurements. If you examine your display or the displays of your oscilloscope, here you could see some information. And this information we have what? Multi-cycle. So you see the pulse, and this is single cycle. Then you see rising edge and the falling edge. Rising edge, say rising edge and falling edge. Rising edge. You will discuss this concept especially in digital electronics. Because rising edge or rising time and falling times is very important. Even whenever you will be writing programs, for example, of some of the sensors, for example, coin acceptor sensor, you have to know about raising, whether you are dealing with raising or falling. So raising, it means that when the signal raises up. And then falling, when the signal falling. So there's a raising time and the falling time. Again, so we have what? So falling and raising. So we don't see anything. So to see the measurements of that signal, you have to come and press the buttons which have been written measure. Say measure. Measure. So when I press it right now, you see the reading. So those are the different electric parameters of that square wave, of that pulse. Right? Right? So the first one, what the name of that parameter? Frequency is what? Speak loudly. Frequency is what? 1 kilohertz. And the manufacturer said that when you connected the BNC into this comp probe, then you can get a signal which is pulse and a signal which has the frequency of 1 kilohertz. Is manufacturer true or not true? True. Then, the second parameter, what its name? What the periods of that signal? The next parameter, what is it? Pardon? Main. Main what? Main voltage. It means average voltage. The next parameter is what? The next parameter is what? And the next parameter is what? Next one? Eh? The next one? Rise time. Okay, so mention the measurements of the frequency. Eh? What they measure the period? 1 millisecond. What is the measure the mean voltage? 2.5 60 voltage. What they measure the value of peak to peak? PK to PK, it means peak to peak. Right? What the peak to peak voltage? Then what the measurements of the minimum voltage? Negative 1.2. 0 volt. Then the next parameter is what? Maximum. What the maximum measured voltage? 6.244. What the next one? The pulse what? Pulse what? Pulse position width. That's the meanings. Pulse is the abbreviations of position width. Okay? So you see those measurements. So then if you want it to alter, you can actually increase the voltage of your signal, but in terms of the waveform. But in case that maybe you find that you've been lost, so this is 60. So there we have 5.4. So there we have 2. They have 5.4 volt. That the voltage of the pulse. So the voltage of the pulse is what? The maximum voltage of the pulse is what? 5.4. So now the position of your waveform is not within the display. So we have moved the waveform because it's been hidden. So if you want to move, you have to use this one, which you call this button, which returns as what? Position. So this one is actual to move the waveform up and to move waveform down. Are we together, class? Are we together, class? Why do we have minimum voltage which is less than the maximum voltage? Shukuru? Why do you have minimum voltage of negative what? Negative 1.12 volt. While the maximum voltage is what? Is what? 6.1. So in case that you are lost, you just come that auto set. In case you are lost, you should not worry. You have to do automatic setup. So automatic setup, then you press another the buttons of 40 of measure. So you press the buttons of measure, you see the measured parameters. So now we have 5.24 volt. So let us move the signal down. So if you move the signal down, you find that you are increasing also the voltage. Why? Because the position is not so the positions is located. It means it's fixed. So you are moving with that with that position. So the negative value is actually the measurement from what? Because we expect it to have a clear pulse, right? But here we have some some noises. So these are the noises. So that's why that we have minimum minimum voltage. Class, are we together? So now we can increase the frequency of the signal, or you can decrease the frequency of the signal. So after doing those measurements, I will teach you how you can interface with. It means in the next workshop I will teach you how you can set up, because all of these measurements you have to set up. The digital oscilloscope itself actually can give you some default measurement, but there's a lot of parameters that maybe you are not interested in. You have to get into the menu and choose the parameter that you want the digital oscilloscope to do the measurement. Are we together? Okay, fine. Is there any questions up that second step of setting the digital oscilloscope? If you have any question, ask it. Is it clear? Good. So now we are disconnecting our BNC connector from the from this default point of measurement. Then we have our step-down transformer. We have to connect it to power. This digital oscilloscope can withstand up to 400 volts. But in case you wanted to examine the waveform of domestic AC of 220 volt to 240 volt, there is a special connectors that you have to connect into the AC mains. Class, listen. Now we are going to the task. We are going to the third part. The third part, now we are going to start the waveform we have discussed in theory and waveform we have discussed in simulation. Are we together, class? Are we together? The first waveform is input from the main AC source. Okay? So this oscilloscope can withstand even that 220 volt, but you need special connectors in order to connect this oscilloscope into the domestic power source. So because we don't have those connectors, we want to measure or want to study the nature of the waveform of the AC mains with that amount of the voltage. Are we together? Are we together? Is it clear or it's not clear? It's not clear. I say the maximum voltage that this digital oscilloscope can withstand is 400 voltage. 400 what? In Tanzania, what the range of the root mean square volt, domestic root mean square voltage? 220 volt to 240 volt. 240 volt is greater than 400 volt. It's less than. Right? So it means that this digital oscilloscope can display the nature of the waveform from the domestic power. But in order for you to connect it, this digital oscilloscope, they are into the AC mains. You need these special connectors to connect it because here there is a large amount of currents which can destroy your digital oscilloscope. Are we together? Are we together? And we say the nature of the AC signal is sinusoidal. So that the first waveform that we've discussed when we've been designing the linear power supply. Class, are we together? Are we together? But in case of the output, there is no problem. Why? Because we are going to have either 12 volt or 60 volt. And the currents, the maximum currents that this transformer can provide is only 1 ampere. So 1 ampere, this digital oscilloscope, you can connect it directly by using the BNC connectors because 1 ampere is actually less than the maximum current that this digital oscilloscope can withstand. Class, are we together? Are we together? As I say no, as I say yes. What the challenge? What didn't you understand? Anyway, in simple language, I can tell you that we cannot use this digital oscilloscope to measure or display the nature of the waveform by connecting direct to the main source by using the probes. Is that clear? I told you that the first waveform is sinusoidal. Right? Which promote the main AC. So the thing that because that's what you have to display. I told according to the manufacturer setup, I told you that we cannot connect this digital oscilloscope with the AC mains by using this BNC probe. So you cannot take this probe and connect direct to power, or you connect it direct to the cable. Why? You are going to destroy the probe, you are going to destroy also the digital oscilloscope. That's the simple point that I was teaching. Is it clear? Yes. Is it clear? Yes. So in order to connect it, you need some special interface. Okay, so let us move. So this is our step-down transformer. The input or the output root mean square voltage, we might get 60 volt or we might get 12 volt. That's according to the manufacturer. But when we measured it, you found that it's not 60.0 and also it's not 12.0. It's 60 point something and 13 point something. Okay? Are we together? So now let me check it first of all if I've connected it or I have AC mains in this power cable. So you have to turn on your digital multimeter and set in AC voltmeter so to check if you have AC source. So the root mean square voltage 227.4 volt. So it's fine. So we can work with this one. So I don't have any problem with shorty with power cable. So the power cable is functioning. So remember that whenever or in any kind of the design or troubleshooting that you are doing, the multimeter should always be your companion to do troubleshooting, to check if there's the right connections or there's the wrong connection. So the multimeter, whether you're using the oscilloscope and function generator, even if the experiments does not need you to use to do any measurements, the multimeter also can help you to troubleshoot and to cross-check your system or your design before you go for the testing. Are we together? Are we together? Okay. So now let me check. Let me measure the output voltage from DC, from the DC step down transformer. So I don't get the reading. Why? Because the transformer, not the transformer, I did not turn on the power source. So the measurement is 60.65 7 volt. Shane, Yoichi, and Shukuru, I gave you a task. You haven't begun. Okay. So this is 60.655. Why did I do this measurement? They aim to know whether the step-down transformer is connected with the main, with AC main. Are we together? Are we together? Okay, so now it has been connected with AC main. So if that's the case, we take the So we have, when we've been setting, we have shifted the signal from the center to another point. So let us reset it back. Let us do measurements. So measurements are okay. So it is connected now. So now we are going to connect our BNC connector with the 2 wires from the step down transformer. So let me connect now with the first one. Then I take another connector of the BNC of the oscilloscope and connect it. So once you are done, then you have to do auto setting. So that is the sinusoidal AC signal from the step down transformer. Okay, let us go. So this is the waveform from the step down transformer. So that's the nature of the waveform. You may also change the way that you want. But in case you want to get the measurements, we have got the sinusoidal. That's what we drew theoretically. If you don't remember what we drew, but for me, what I do remember, we drew a clear sinusoidal signal. And that's what you have there. We got it from the step down transformer. Right? Then you want to do the measurements. So we have pressed the auto set. Then we press the buttons of measure. So once you press the buttons of measure, Now we have what? Our measurements. So those are the measurements from what? Two nearby terminals of the center tape D step-down transformer. So you see the waveform, also you see the measurements. So I told you that in practical, in workshop, or in practical electronics or in workshop, you should record the information. So now it's the time to record. So the first parameter is what? A frequency. What the frequency there? I say, please mention when you're recording. Hurry up, please. What the frequency there? Pardon? What the average? If it's varied, what the average? A? Write what you see. So others you write 50, others you write 80. But remember that. That 50 is not measured by the frequency meter from the digital multimeter. That 50 or 49 point something is measured by using the oscilloscope. So sometimes you might be asking to measure the frequency of the signal, and then you'll be asked to use the oscilloscope. So don't say that, oh, oscilloscope does not have the frequency meter. Who told you? Simply just say that you don't know oscilloscope. Then the next parameter is what? Period. What the periods of that signal? 20 what? Millisecond. Remember the default signal, the periods was what? 1 millisecond. Right? Right? Class, draw the waveform that you see, record the reading. But you should not record because you will measure yourself. You should not record from your table. Record roughly. So when you be doing, you can check what you have found and what you have measured. You are sitting like wonderful bosses. The next parameter is what? Mean. What the mean voltage? 800 millivolt. Right? The next one is what? Peak to peak. What the peak to peak voltage? 20.2 volt. That the peak to peak. Right? What is maximum voltage? 10.20 what? 10.60 volt. That's the maximum alternating voltage. Are we together? Are we together? Yes. So from there, a serious and a focused student could have asked you some questions himself or herself. Which kind of the question? The manufacturer said that if you measure the output root mean square voltage from the step-down transformer by using the two near wires, you will get 60 volt. Are we together? 60? So that is theoretical value declared by the manufacturer. Then we went for the simulation. For the simulation, okay, we did some setting and then we might get 60 volt because we just changed the primary inductance and secondary inductance of the transformer that you are going to get in the simulation software. Okay? Okay? When we moved into the practical, by using the digital multimeter, if you do remember, we measured that the root mean square, the output root mean square voltage for this case is what? 60.6072. And now I'm measuring it again. It's 60.671. Are we together? So remember that. The manufacturer said the same root mean square voltage is 60 volt. Simulation software gave us another measurement. And then this digital AC voltimeter also gave us the measured root mean square voltage, but also the oscilloscope gave us another maximum voltage. So the maximum voltage is what? 10.20. 10.20. So what can you tell me? What happened there? Why there are the variations or there's a difference in those measurements, in those parameters, or in those measuring instruments? Do you think that the measuring instruments has a problem? Or do you think that the components or the step-down transformer has a problem? Or do you think that you are the one who has a problem? What do you think? The manufacturer said what? 6 what? 60 volt. We measured that is 6 what? 6.677 volt. Right? And then the oscilloscope tell us 10 volt. What happened there? What could we say as electronics and telecommunication engineer? What could you say? Hey, who can try? Welcome. Speak loudly.
I think the value that we get from the multimeter is root square value. But the reading which we have outside from the oscilloscope give out the maximum voltage from that we have acquired from the multimeter. When you come to get about the 9 point something or 10.
Then the manufacturer value? He said 60 volt. What the means of that 60 volt? What the name of that 60 volt?
6 volt is
root mean square volt. So the manufacturer said that my step down transformer will give you 60 or root mean square voltage of 60 volt. Right? The digital multimeter measured the 60.677 volt. But that is also root mean square voltage. The oscilloscope measured the 10.20 there. 10.20? 10.8 volt. But it is what? Maximum voltage. So there is no any huge deviation. It's just the two parameters within the single testing point. So it means the manufacturer stated the root mean square voltage. The digital, the AC voltimeter also measured what? The root mean square voltage. But the oscilloscope measured the maximum voltage. Are we together? So the engineering students of Molo or Horo or Rao is right. So let us now congratulate him. That's the answer of that question. But before we congratulate him, I know some students in this class still have an argument. Just take 60.677 multiplied by under root of 2. Because root mean square voltage is equal to the maximum voltage over under root of 2. Or in order to want to verify the reading we have got it from the digital oscilloscope, it's 10.82, that's the maximum. Divide by under root of 2. Then you get the root mean square voltage. Do it quickly, it's simple mathematics, there's no need for the scientific calculator. Under root of 2 is what? 1.14? 1.414. Divide by 10.8. Divide by 1.414. What did you find? So what the root mean square voltage from the oscilloscope? Student, I'm talking to you. So you don't have even scientific calculator? 7.6. So the root mean square voltage given by the oscilloscope is 7.20.6. So 7.6. There we have 60.63. That's the goodness of practical. Because in practical, the same testing point, you get different readings. And you have to reason why. And that's why that you're an engineer and you have to think different. If you cannot think differently, we ask you to go to another field. Because now we are dealing with only a single parameter. We have already confused you. So which is true? 60 volt? Or 6.67 volt? Or 7.20.6 volt? Which is true? Class, which is true? All are true. Both. We use both when you have two things. We have three there. So. Okay. So from today onwards, you have to know that the AC voltimeter gives you the root mean square voltage. The digital oscilloscope gives you the maximum voltage. If you fail to confuse, if you fail to differentiate, you are going to confuse and you are going to panic. And you will hate the subject of measurement. Also, be a political, electronics and telecommunication what? Engineer. Okay. So then, I'm going to change the leads. I'm going to measure now Because I measured, remember that the center tape, this step down transformer, it has 3 wires. These are the first 2 wires, and we have also another wire. So before I measured it between the first wire and the second wire. So now I'm going to measure the second wire, the first wire, and the third wire. Okay? Which manufacturer told us if you measure the root mean square voltage given by step down transformer will be what? 12 volt. Right? When we measured by using a digital AC voltmeter, what did you get? 13.20 something. Right? So let us now ask the digital oscilloscope to display the waveform and also to do the measurements. Are we together? Are we together? Ask your neighbor, is electronics and telecommunication engineering beautiful to you? So the answer is yes or no. So ask your neighbor. You don't want to ask your neighbor. Okay, ask yourself. So tell yourself, my mind, is electronics and telecommunication engineering beautiful or not beautiful? Okay, so now we are going to use, or we are going to do the measurements between to measure the root mean square voltage across the blue wires. So then I want now to see what we have found. First of all, remember that the maximum voltage of 60 volt, or the maximum voltage of root mean square voltage of 60 volt is less in peak rather than the one of the 12 voltage. Have you understood what I said? No, others did not understand. Check the nature of waveform when we've been measuring the voltage between the wire number 1, number 2, number 3. What do you say? In center tape D, step down transformer, this is the output part. Keep quiet. Keep quiet. So we have 3 wires for the output. This is number 1, number 2, number 3. So the manufacturer said that the root mean square voltage at this point will be what? 60 volt. And at this point also will be 60 volt. So also the nature of the waveform. The nature of the waveform between terminal number 1 and terminal number 2 is less than. It means that the peak or the nature is small than. It means that the waveform here is smaller than the waveform between terminal number 1 and number 3. Are we together? Are we together? And you want to verify. How can you verify? Just see when it has been like this way, you see the nature of the waveform, and now we are going to change. So when you are going to change, then you will see even the nature of the waveform will change. How will it change? Theoretically, you expect that the magnitude of the waveform will increase. Means that it will grow. Okay? So now I'm going to change, you will see, and you have to check the waveform first. So you see what happened. Does the waveform increase or decrease? Or remain constant? Eh? Eh? So it is true theoretically. Right? Eh? Because the first one is between number 1 and number 2. The second one, number 1 and number 3. This, the root mean square, here it is 12, here it is 6. Are we together? Are we together? Are we together? Okay. So now we are going to, we have our measurement. What do you see there? Do our measurements change? Eh? Eh? Do our measurement change? Which parameter is changing? Frequency remains the same. It means that the output frequency is still 50 Hz. Right? Then the period, the same. The mean, the same. The maximum voltage, okay, let us start with peak to peak. Peak to peak voltage there, it is what? 40 volt. It has changed or no? It has changed, right? And then the maximum voltage, 20. Previously it was what? 10. If you take 20 and something divided by under root of 2, Edison, do the division of the numbers. Class, is it clear? Eh? Eh? So, do you believe that the alternating voltage, the domestic alternating voltage, and the output of the step-down transformer is sinusoidal? Have you believed it today? Eh? Yes. You saw it. Because if it is a pulse, you will see a pulse. If it is square wave, you will see a square wave. If it is sawtooth, you will see a sawtooth. If it is ramp signal, you see the ramp signal. If it is unit signal, you will see the unit. If it is DC, or it means constant signal, you will see the nature of the constant signal. Are we together? Are we together? So tell your neighbor that electronics engineering has worked and I'm still alive. Okay, alive. You just said it with alive. So now we are going to the next step. So we have already verified the nature of the waveform from the step-down transformer. Remember that I will give you the oscilloscope. You have to show. You have to demonstrate. We don't need politics in engineering. Okay? So the next step now, if you remember the waveform that we drew, the output of the step-down transformer will be the input of the bridge rectifier unit. Right? 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 So now let us build our bridge rectifier circuit. So bridge rectifier circuit, this is the first diode, this is anode, and this is cathode. Then I take the second diode, I connect anode of the second diode with the cathode of the first diode. Then I take another diode and connect it with the cathode of the first diode, and I take the first diode and connect it. So the anode, connect the anode with anode, and then connect the cathode with anode, and they have a common cathode. Okay, so here it's the bridge rectifier. Student, keep quiet. We are still continuing. We are serious. This is our bridge rectifier unit. So Shane has gone out. And the number of students has gone out. That is good. Okay. So I think that wrong connection. Okay. So another thing which I want to tell you that which I did not tell you that it's better before you use your material, it's better to check if the diodes are live or they have already burnt. So you have to take a digital multimeter and you set it into the continuity tester. No, into the diode tester. So you have a diode tester. If you measure the potential barrier is 6 point something, that diode is active. When you measure and give you OL, that's not active. Okay? Are we together? Okay, so I think that's better to check to display the what? But you have to make sure that the positive lead, the red lead is connected to the anode of the diode. So now, just zoom this the display of the multimeter. That's why I told you that you need multimeter for your experiment. Or sometimes if you find a challenge, you can just use the breadboard to do your measurements. You just connect them without taking care. So now the potential barrier is 0.600. What? What do you see there? 0.6015. So that diode is active. It's working. Okay? If you reverse, you will see that. What will you see? OL means over limit. Fatima? Okay. Then I'm going to check the second diode. Because if you don't check them, you'll be expecting to get the waveform in the oscilloscope while the diodes are not working. So now the measurements, the potential barrier is 0.5968 volt. Okay? This number 2 is fine, is okay. Then Let us do measurements for the next one. Then this is 0.6041. Rafa is going out. Then let us measure the fourth one. Rafa has gone out. Why he has gone out? Because he understands what we are doing. So this is 0.597 2 volt. So all the 4 diodes are working. Okay? Okay? Okay. Say that, oh, I like electronics engineering, but I don't like measurements. Or measurement is too tough. So measurement is too tough. So what do you think that is simple? You have to make sure that when you connect your diodes, you have to avoid the short circuit between them. Because if you do the short circuit of the diodes, then you will find that you are going to burn the step-down transformer and you are going to burn all the diodes. So you have to be careful. So the next step, we come back to our oscilloscope. We still have our sinusoidal signal. So we can turn off our power. So when we turn off our power, we disconnect our probe. Then we take this one and connect it in between or at the anode and the cathode of the first and second diode. Again, sometimes if you have a number of jumpers, you can just separate them. But let us just use it without using the number of jumpers. Let us assume that you are not given enough number of jumpers. So next, remember that. So look here, this is the common cathode, where we are going to call it positive, terminal of the bridge rectifier. And this is the common anode. Okay? Okay? So, if that's the case, so remember that when you are studying the waveform of the bridge rectifier, or Molo is talking, when you study the waveform of the bridge rectifier, you have to make sure that the bridge rectifier, it is connected with the filter unit. Right? So now we have connected the bridge rectifier with the filter unit. So the bridge rectifier unit is connected with the bridge with the filter unit. So the output of the bridge is fed into the input of the filter. So what is the nature of the waveform according to the theory? Pulsating again. The nature of the waveform from the filter unit. Pardon? Unfiltered or unregulated what? Unregulated signal. Or a DC signal contains some ripples. Are we together? Are we together? So now, we are going to connect it. So we still have there. And then we have to press the auto set. So once we press the auto set, your AC is doing something like your AC. So this is pulsating signal. No, this is unregulated signal. How do you know that it's an unregulated signal? It's not a DC signal. Simple. Just press the buttons of measure. Press the buttons of measure. Do the measurements. So if you do for the measurements, then now, look on the blackboard. I will kick your head now. So the first parameter is what? A frequency. So if it is frequency, then what do you see in the frequency? Just zoom. Zoom this display. What do you see the frequency? A question mark. It means that signal does not have any frequency. That's the meaning. Then the next signal is what? Period. What the meaning of define period? What is period? Period is a reciprocal frequency. That is the simplest definition. But period is the time taken to complete one what? cycle. So we don't have any cycle there. That's why the question mark indicates that there is no period in that signal. Everything there has a meaning. And everything there is a topic. Then the next parameter is what? Mean. What the mean voltage? 17.2. 17.2. The next one? Peak to peak. What the value of peak to peak? 1.0. 1.0. 1.6 what? Volt. What does it indicate? The DC signal still contains some AC components. That's why you have peak to peak. Because you see this signal is like a noise. It's not a clear DC signal. Are we together? The next parameter is what? Edison? The next parameter is what? Minimum. What the value of minimum voltage? 16.8 volt. Next, maximum what? Maximum current or maximum power? Maximum. And what is the value? 18.0 volt. 18.0 volt. 18.0 volt. Do you remember the measured value? The measured voltage from the filter unit? You remember it? So for you, until you cross-check, give me the range when you measure the output of the filter unit. 17.20 something. Others 18.20 something. And you see there the digital oscilloscope telling you the same story. But if you forgot, that is fine. We have a digital multimeter and this is DC signal. So we have to measure the voltage across the filter unit. So for the digital multimeter, read SOT, read C, how many volt? 16.573 volt. Electronics engineering is beautiful. Are we together? If you forgot, Other says that, sir, no, you are lying, you are measuring another point. It is what is 16.6022 volt. So you don't have actual, okay, there's a difference of almost 1 volt point something, but that's not a great deal actually. You see that there is a relationship between your measuring instrument. The next parameter is what? The next parameter is what? Post width. Then you have what? A question? That signal does not have what? That's the meaning. The next parameter is what? Direct current. Pardon? Rise time. That signal does not have what? Class, is it clear? Okay. Do you have any question? Do you have any question? No. So now we are going to study the waveform from the voltage regulator. So stay tuned when I'm just connecting. Okay, Jimmy's daughter? Yeah. So then I have pressed the auto set. So we have to wait. Then we have our DC signal. The question is, what the difference between the signal from the filter and the signal from the voltage regulator unit? They look like the same, eh? That's according to you. But according to this measuring instrument, always they speak the fact. So the next is say, press the buttons of measure. That's the point where you distinguish. The first parameter is what? Frequency. What the sign? Question mark. What the frequency of the what? Of the DC signal? Infinity. Right? I told you. If you forgot, refer the notes. Then the periods, there is no period. Then mean. Do you have mean? Mean is 5.36. Then peak to peak is what? 1.6. Then maximum is what? Maximum is what? Minimum is what? 4.8. So if that's the case, we can just rotate for a moment. So that's the reading of the voltage regulator unit. What the maximum value there? 5.12 voltage. Is it within the tolerable range? Yes. Manufacturer say that if you measure 4.98 or 4.8 up to 5.2, that is acceptable range. Right? So then 5.12 volt, is it within the range? Yes, so that is a DC signal. So in order to avoid you from the confusion, let me just show you. That is the DC. Do you see the positions of the DC? Do you see the positions of the waveform from the voltage regulator? So let me go back to the filter. So remember the position. So do you see the positions for the filter? It's up. Right? Why? Because its maximum voltage is higher than the maximum voltage of 40 of the output of voltage regulator. Class, are we together? Yes. Are we together? Why not? So to quickly remind you, this is the point. So I can quickly remind you about what we have been discussing. The first waveform that we have discussed is the output of the step-down transformer. Output of the step-down transformer. Output of the step-down transformer. And then we say theoretically, the nature of the signal is sinusoidal. Four waveform, which have been learning theory, and which have maybe you can learn through the simulation, and that is all, and at the end of this workshop. So I don't know if you've understood, but I think that some students say that no, for the output of 40 of the voltage regulator. So we say that the difference between the filter and the voltage regulator is actually the maximum. So now let's give some noises. In case you have any question, please ask it. So there is no any question. So I believe that you have learned, you have understood. It's a time for you now. We'll be having this one as the reference. So I think that we'll be using different oscilloscope. But in case you get a challenge, this oscilloscope is working perfectly. So you should not worry about it, how you can study the waveform. So if that's the case, it's the end of our workshop 9. May God bless you. Did you understand? Yes. Okay, so let me appreciate you. I always appreciate you. I always appreciate you. I don't know if you yourself also appreciate people, but for me, I always appreciate you. So 1, 2, 3. Wow. Do you want to appreciate somebody? Who? Me. Okay, you're welcome. Wow. Okay, I'm very happy because before I taught you this concept, I was sick. So now I'm kind of fine. Because I've been telling you the facts, but I've never verified. So I'm very happy. I think it's the time for you also to practice. May God bless you. See you in the next workshop.